Okay, we will briefly look at Fourier transform properties. So many of them are familiar to you already from the Fourier series. So we will not look at all of them. We will look at some of them only. For the remaining, please you can look at the textbook. And there are more examples also in the textbook. We will look at a few of them in this lecture. So one property which we have seen earlier is that of linearity, which you have seen also in the case of Fourier series. So if x of t transforms to x of omega, y of t transforms to y of omega, a linear combination a x of t plus b y of t transforms to a x of omega, b y of omega. So this also gives you the notation. So usually if you have an x of t, its transform is written as x of omega. Okay, so if there is an x of t, its transform is written as capital X of omega. Okay, so if there is some symbol s of t, its transform is capital S of omega. That is the convention usually followed in various books. The next property is that of time shifting. So if x of t transforms to x of omega, and that is x of t has the Fourier transform x of omega, the time shifted x of t minus t naught gives you e raised to minus j omega t naught x of omega. Okay, so this property we have seen also in Fourier series. So essentially what this means is that the time shifting does not change the magnitude of f of t, because the magnitude of this is 1. Okay, it only changes the phase. So if this is a complex number, it will have a magnitude and a phase. It will have, if you write this in polar form, right? So now this will, when you do the time shifting, only the phase part will change. The magnitude will remain the same. The next property is that of differentiation. If x of t transforms to x of omega, d by dt of x of t transforms to j omega x of omega. So this is the differentiation property. Okay, so this x of t as this is the Fourier transform pair, then the Fourier transform of the derivative of x of t is j omega x of omega. The next property is that of time scaling. See, all these properties are very simple to prove. Okay, that goes directly from the definition of Fourier transform. So if you apply this into the definition of the Fourier transform into the analysis formula, you will get the required property. Maximum you might have to do a change of variable. So please, you can look at the textbook for the derivations. So the next property is that of time scaling. X of t transforms to x of omega, x of a t, which is a time scaled version of x of t, transforms to 1 by a x of omega by a. Now an important property which we saw again in Fourier series is that of convolution property. That is, if y of t is the convolution of x of t and h of t and x of t, then the Fourier, this is in time. So these operations happen in time. So essentially this is convolution which is happening in time. Okay, then what will happen? How are they related in frequency? So if you take the Fourier transform of all this y of omega, this convolution operator now becomes a multiplication operation. So this is h of omega, here is the Fourier transform of h of t, and x of omega is the Fourier transform of x of t. So essentially what this means is, when you convolve in time, you multiply in frequency. So this is a very useful property of the Fourier transform, which we will use in various cases many times to get the output of a system instead of convolving it in time. Many times it is easier just to take their Fourier transform and multiply. We will see a couple of examples. These are examples again from the textbook. Example 4.15. So there is this system h of t which is got, there is a system which has an impulse response h of t, which is del of t minus t naught. That is this, which is basically a shifted impulse. Okay, so this is the impulse response. So that means that is an LTI system. If you give it a delta function as input, this is what you get as output. This is the impulse response. So now if you take the Fourier transform of this, okay, what will be the Fourier transform of this? So you know already from the previous class that the del of t delta function has a Fourier transform which is 1, which is constant across all frequencies. The delta function contains all frequencies, and del of t minus t naught is nothing but a time shifted delta function. And from the time shifting property which we saw here, you will get now if this is t minus del of if del of t has a Fourier transform equal to 1, del of t minus t naught will have a Fourier transform e raised to minus j omega t naught multiplied by 1, which is essentially ef minus j omega t naught. So this is the Fourier transform of this. Okay, so this one has a Fourier transform this. So now if you want to know what is the output of this system, of this LTI system, which has the impulse response, what you can do for some arbitrary input x of t. Okay, if you give this input, what is the output? One way is to convolve this in time, convolve x of t and h of t in time, and you will get the output. That will become your y of t. The other way is to do it in frequency. You take the Fourier transform h of omega, which you already computed it here, and x of omega, which is the Fourier transform of x of t, and you multiply. Essentially this will give you, this is h of omega, this is x of omega here. So this is nothing but, this is again if you apply the time shifting property here and you take the inverse Fourier transform, you get y of t equal to x of t minus t naught. Essentially this means that if this is the impulse response of the system, if you give some arbitrary input x of t, you get the output x of t minus t naught. Essentially it is a system which is a delay. This is the impulse response of a delay system, and this is the output for any x of t. So at this point, I hope you remember what we said, what is frequency response. So if you said, so if you remember the definition in equation 3.121, the previous chapter, frequency response we said was this. This was what we defined as the frequency response, where h of t is the impulse response of a system. Okay, so the frequency response of a system is this. So now after you look at the Fourier transform and after you have studied the Fourier transform, essentially this expression is nothing but the Fourier transform of the impulse response. So essentially the frequency response of a system is the Fourier transform of its impulse response. Okay, so please keep that in mind. Then one more example, example 4.16. If x of t, there is a system, x of t output y of t, the relationship between x of t and y of t is like this. There is a differentiation. So the system it's a differentiator. The system differentiates it. And now if you want to know what is the frequency response of the differentiator, again you can use the convolution property. So if you take the Fourier transform on both these sides, you get y of omega equal to h of omega, which is the frequency response of this, into x of omega, yeah, which is the frequency response of the input. But we know from the differentiation property that y of omega, for a differentiation system, if x of t transforms to x of omega, d by dt of x of t transforms to j omega x of omega. So essentially this means that the frequency response of the differentiator is j omega. Okay, so this you can try. These are examples illustrating the use of the various properties of Fourier transform to solve some problems. Another example is again to give you a physical meaning of what all this is doing. So this is some example, this is some picture which I got from the internet. So there is a singer, she's got a voice x of t. Let's assume that this voice can be represented by x of t. There is a microphone here which has an impulse response h of t. Okay, so now if the operation of the transduction by the microphone can be modeled by a convolution, if the relationship between the voice and the mic can be represented by a convolution, let us assume for the moment that it is possible, then the output of the microphone is nothing but the voice convolved with the impulse response of the mic. Okay, so this is what is the wire of the mic carries that signal, and it goes to, let's say, an amplifier. Okay, now let's suppose the amplifier outputs a of t, and it goes to a loudspeaker, which has got its own impulse response, which is h2 of t. So now the relationship between a of t and h2 of t is, again we can assume that it is a convolution. So the final output is going to be a of t multiplied by h2 of t. Okay, that is the output which comes out of the loudspeaker. Okay, so here we have modeled the operations by convolution, so that you can get a physical feel. So here we are convolving. So, but if you take the Fourier transform of all this, if you take the Fourier transform of the voice, Fourier transform of the mic, then this becomes a multiplication. X of x, this becomes x of omega, h of omega, and this becomes a of omega multiplied by h2 of omega. This will be the Fourier transform O of omega. Now, if you want to get the output, you take the inverse Fourier transform. Okay. So, if the operation between a signal and a system can be modeled by a convolution, then you can use the convolution property of the Fourier transform to determine the input and output relationship. Another example, example 4.18 from the textbook. This is the frequency response of an ideal low pass filter. Essentially, it means that it is a square pulse with a cutoff at minus omega c and plus omega c. Essentially, it means that which has got a gain factor of 1. So, essentially, this means that it passes anything between 0 and minus omega t c to plus omega c unhindered, whereas anything above this will be attenuated to 0. Right. So, this is an ideal characteristic of an ideal low pass filter. And we have seen earlier that if you take the inverse Fourier transform of this, you get a sink. We saw also the duality between the square pulse and the sink. So, this is the sink, and this we said about this earlier. So, this is the impulse response of the ideal low pass filter. Okay, and we said that this ideal low pass filter, because by looking at the characteristic itself, since it has non-zero values at time less than 0, this is a non-causal system. Okay, this system is not causal. So, in practice, it is probably not realizable. It is not possible to realize non-causal systems. And also in this case, the sink has oscillations. So, there may be some cases or some applications where this kind of oscillatory behavior is not required. For example, if you are doing audio filtering, then you don't want your output to oscillate. You don't want your output to have ups and downs. Okay, so in various applications, it may not be desirable to have this kind of an impulse response. So, an approximation to an ideal low pass filter is a non-ideal low pass filter which has got this impulse response. This impulse response, because this impulse response is easy to implement, because first of all it is causal. Okay, this impulse response is given by this one, e raised to minus t ut. So, this becomes causal because less than 0 it is 0, and it is a smoothly decaying input. It is not something which oscillates. Okay, so this depends on the application, but there may be some applications where you don't want oscillations in the impulse response. So, the frequency response of this is like this. If you take the Fourier transform, you will get this expression. And when compared to the ideal low pass filter here, which has got sharp cutoffs here after omega c, it's completely attenuated. Here you don't get the sharp cutoff. Okay, so here you can say that after some point the attenuation starts, but the attenuation is not very sharp. So, that is the trade-off which you have. So, based on the design constraints which you have, you may be able to, you might want to choose several parameters to decide whatever is best for your application. Another example 4.19, it shows the use of the differentiation the convolution property to solve convolution problems. Okay, so for example, in the second chapter we had looked at several ways to convolve two signals. Okay, there is an h of t and there is an x of t. If you want to convolve them, you have these two signals which they have given here. So, you can keep one fixed and flip the other one and do the convolution which we had done. So, that convolution we were doing in time domain. Okay, but by using the convolution property of the Fourier transform, it may be sometimes easier to do the convolution in frequency. So, basically, if you have this y of t as h of t convolved with x of t, in frequency domain it becomes y of omega equal to h of omega multiplied by x of omega. So if you take the Fourier transform of this, x of omega will give you this, h of omega will give you this. So there is a table in the textbook which lists common Fourier transform pairs. This is the time domain, this is the frequency domain. There are two columns. You can look at that table and get these Fourier transforms. And then your y of omega will now become x of omega multiplied by h of omega, which is this, right? So now how do you find the y of t? We need to find the inverse Fourier transform. For this, one way is to, when you have this kind of an expression, one way is to use a partial fraction expansion. So that we have done it here. You take two variables a, b, and then now you have to find out the values of a, b such that this is equivalent to this. Okay. So one way to do this is remove the conjugation to multiply with the complex conjugates and equate the LHS and the RHS. And if you do that, in fact, you will get a equal to minus b, which is 1 by b minus a, where a and b are these. So essentially your y of omega is now this, okay, 1 by a plus j omega minus 1 by b plus j omega. This is your, so your constants a and b, you got it as 1 by b minus a, and the relationship between a and b is a is equal to minus b. So just now that if you know that if you have the Fourier transform like this, by looking at the table of inverse Fourier transform, you can find out what is the inverse Fourier transform corresponding to this, and that is nothing but here by looking at the table or by inspection, you can see this has the inverse Fourier transform e raised to minus at ut, and this has an inverse Fourier transform e raised to minus bt ut, provided b is not equal to a. Okay, so this becomes my y of t. This is nothing but two decaying exponentials, two causal decaying exponentials subtracted and scaled. Fine. So that was the so when you convolve these two signals in time, you get this signal in time. That this final signal you get by taking the inverse Fourier transform of y of omega. We have applied the convolution property here. So equivalent to the convolution property, there is a multiplication property. So what always remember the duality, okay, Fourier transform. So we said that when we convolve in time, it is equivalent to multiplication in frequency. Similarly, when we multiply in time, it is equivalent to convolution in frequency. So that is what we will see here. So suppose there is a one signal like s of t and another signal p of t. Okay. So when you multiply this s of t multiplied by p of t, if you take the Fourier transform, it is actually 1 by 2 pi s of omega convolved with p of omega. So the Fourier transform of this r of t is nothing but the convolution of the Fourier transform of the two signals which we are using for the multiplication with a scaling factor of 1 by 2 pi. So this can be illustrated here for a application in communications. So suppose there is some signal here which has got this spectrum. This is the spectrum of the signal. So you can so this signal is band limited. Yeah? The bandwidth of the signal here means that the difference between the greatest frequency and the lowest frequency. Okay, so this here in this case, it is 2 omega 1 is the bandwidth. Okay, and all the other frequencies are all 0. So the signal is restricted to this band. So suppose there is such a signal, and the spectrum of the signal looks like this. So this is some arbitrary spectrum. We have just shown this picture here illustrates that this is the important part of the spectrum is between this. So no matter what the shape is, that we don't have to worry. Okay, so this is between minus omega 1 and plus omega 1, and it has got some scale a. So this is my s of omega, which is this Fourier transform of s of t. Now I am multiplying here in time, so I should take the frequency, I should take the Fourier transform of p of omega, that is p of omega. So here p of omega is cos omega naught t. So the Fourier transform of cos omega naught t is this, which we have seen in an earlier example. Okay, so there are two delta functions at minus omega and plus omega. So when you multiply these two, essentially in frequency domain, this and this gets convolved. So it is like convolving this signal with this signal. So again, from convolution examples, you know, when you convolve two signals with convolve a signal with two delta functions, the signal will get repeated here and here. Okay. signal gets repeated here, and there is a 1 by 2 pi factor here, which gives me the scale a by 2. So this is my Fourier transform of the product SFT into PFT, right? So if I want to get the RFT, I take the inverse Fourier transform of this. This is R of omega. So now this is what is used in communication. So basically what has happened is the whatever spectrum is there here has now been shifted to higher frequencies. That is essentially what has been happened. This is what is done in the idea of modulation. When you do modulation, when you do all your mobile phones and or AM radio, FM radio, all of them modulate. So a message is modulated by a carrier. A carrier is usually a sinusoid. This is the carrier. So the carrier is modulated by the message, and this is essentially what happens. The spectrum of the message gets translated or shifted to a higher frequency. It is more efficient to transfer higher frequencies. So now, so this is my R of omega. Okay, now suppose I take the inverse Fourier transform, I get my R of t. Then I suppose I multiply R of t again with a carrier cos omega naught t. Okay, R of t I am multiplying again with PFT. So again, we can do the operation in frequency domain. So this is my R of omega, this is my P of omega, right? So this multiplication now becomes a convolution, which gives me my G of t, which is the G of omega here, 1 by 2 pi R of omega convolved with P of omega. So here we need to convolve this with this. Okay, when we convolve that with that. So just to illustrate the steps, I can do the operation in time domain also. Essentially this is multiplication. So this is S of t multiplied by cos square omega naught t, because P of t and PFT are cos omega naught t. So this is by using the using the formula, I can write the cos square omega naught t as 1 plus cos 2 omega naught t, half of st into 1 plus cos 2 omega naught t, and if I just simplify this, I will get my g of omega as half s of omega plus half s hat of omega, s tilde of omega. Okay, so this is my s of omega. S of omega is nothing but my original signal. This is the Fourier transform of, I get my s of t, it transforms to s of omega, and hence so I will have a term here s of omega, and I will have another term here half of s tilde of omega. S tilde of omega is nothing but your this one, your R of omega. Okay, so if you write down the expansion, it's just 2-3 lines, you will get this, and there is a half factor here. So the spectrum of your output looks like this. Okay, so essentially what did we do? We had an original signal which was like this. It had a spectrum here. Then we modulated it, and the spectrum shifted to higher frequencies. So now we have two copies of the spectrum at higher frequencies. Then I multiplied this again by the carrier, which is the cos omega naught t, and the resulting signal was like this, which has the original signal spectrum in the original place and two extra components here which come as a result of this. So now if you apply a low pass filter here, ideal low pass filter or some low pass filter which has a cutoff which includes this range, then you can isolate and get this part back. So these two things will get eliminated, this and this go off, and you get only this, and so you will be able to get back the spectrum of the original signal. So this is essentially what we have done, is we have described the operation of a modulator and a demodulator, basically a communication system. There is a receiver which there is a transmitter which modulates, and a receiver which demodulates. So this is the principle of that. So this illustrates how the operation of LTI systems can be viewed in both time as well as in frequency domains. Fine. So this kind of covers several topics in Fourier transform. So for more examples and more material, please refer to the textbook. Please try to solve all the solved questions in OpenHand. Okay, you can solve the exercise problems also should be solved if possible. Please do that also, but definitely the solved problems, please do try to solve. Okay. Thank you.